All right. So far, we talked about the magnetic field created by a moving charge, given by this formula, and this is the pattern. It's going around the velocity vector, and also a current element, a piece of wire that has a current I in it. It behaves exactly like that. The magnetic field is exactly like that of a charge moving, because IDL is the same as Q times V. And this is called Biot-Savart's law. And if you integrate over a piece of wire, you can find the magnetic field at this point, which is the perpendicular distance to one end of the finite wire, the distance r. You can get this formula, which is mu naught I over 4 pi r sine theta. Theta is the angle, viewing angle of the wire from this point, from this side to the other side. If you let this become an semi-infinite wire, then sine theta becomes 1, then you get mu naught I over 4 pi r. And if you have an infinite wire, then you have twice that, which is mu naught I over 2 pi r, which is this. And this figure shows how the magnetic field actually behaves around, or pattern of magnetic field around the long straight wire carrying current I. All right, and then we talked about the interaction of two long straight wires, that they apply a force of this magnitude per unit length, mu naught I prime divided by 2 pi r. Actually, this is just BLV, right? BLI, because one of them is has a current. One of them creates a magnetic field, and the other one that has current in the magnetic field feels a force, and vice versa. So the two currents, when they are in the same direction, they attract each other. And if they are in the opposite direction, the current are in the opposite direction, they repel each other. That actually sheds light on why magnets, if opposite poles of magnets attract each other. Because when you have poles of magnets like that, you have north and south pole. When the currents are in the same direction, you have north and south in the vicinity of each other, and they attract each other because the currents are in the same direction. And the same in here. And therefore, the same when you have two magnets. I explained that in the previous lecture, so I don't go into details again. And when the two magnets have the same poles toward each other, the currents in the magnets are in the opposite direction, so they repel each other. That's why the same poles of the magnets repel. And then we derived, or didn't derive, we talked about the magnetic field created by a loop of current on the axis of the loop at the distance z from the center is mu naught I r squared divided by 2r squared plus z squared to the power 3/2. And when you have n turns, you just multiply that by n, because the magnetic fields just are in the same direction, add up. And if you have a loop of current and current I going through it, but you are at the center of the loop, means z is 0 in this case, or in this case, then this simplifies to mu naught I over 2r. And with the definition of magnetic dipole moment of the coil, which is NIA, we can write the magnetic field of this coil as mu naught mu over 2 pi z cubed, which falls off with the cube of the distance when z is much larger than r. So that applies for anything that is small, but it has a magnetic moment. And if you have a circular arc of wire, current I passing through it, this magnetic field at the center becomes this, mu naught I over 2R, the same as before. It should be capital R, 2R times phi over R, phi over 2 pi. So this, in fact, should be written this way. This should be capital R to begin with. And you can write it as, let me take this out and put that here, and over the 2 are the same as what we had for the wire, then divide by this. Oh, shoot. Oops, it goes up here because I didn't put it. All right. You see, now this should be 2. So you see, this means the same fraction of the circle that you have times the formula that you had here, be mu naught I over 2R. So mu naught over 2R times phi over 2 pi means the same fraction of the circle, the complete circle that you have. Phi should be in radians here. All right, so it should be like that. And then we talked about Ampere's law that says that if you calculate the integral of B dot dl around any closed loop, that becomes equal to mu naught times the total current passing through that loop. It's similar to what we had in chapter 23 about Gauss law, but it's different. Gauss law was about the surface integral of E dot dA, which is equal to 1 over epsilon naught times the total charge inside the closed surface. Here we have integral of B dot dl around a closed loop, and it's equal to mu naught times the total current enclosed in that loop, of course, in one direction, which is considered positive, in the other direction is called negative. It depends on which direction you integrate around the loop. And then we applied it to this situation where we have a cylindrical wire having current I through it, and the current is distributed uniformly over its cross section. We say that the magnetic field again looks like before. It's azimuthal, it means tangent to the circle, centered at the center of the axis of the wire, but the magnitude changes like this. At the center, we have 0 magnetic field. At the surface, we have maximum. And inside, it goes from 0 to that maximum linearly, like a line. And from the surface going away becomes mu naught I over 2 pi r. It reduces by inverse of distance to the center. All right, so this was the result of applying Ampere's law to this problem. And Ampere's law can be applied to an ideal solenoid, and we use this loop, this closed loop for it. And if you apply Ampere's law to this, you can find the magnetic field to be mu naught Ni inside the solenoid, which is uniform, and N is the number of turns per unit length of the solenoid, number of turns of wire per unit length, and each one has a current I in it. So there are lots of currents going around. And of course, ideal means that this goes to infinity on both sides, and that's of course not practical. In practical terms, you see that in practical situations, you have a short solenoid, and here is the plot of the magnetic field along the axis of the solenoid, and which is at the center. It is almost the same as what this predicts for the ideal solenoid, but it is a little bit less because there is less current distribution, and it changes like that. All right, and then we did a step further. I calculated the magnetic field of a short solenoid on the axis of the solenoid. The solenoid is extended from Z1 to Z2, and we came up with this equation, B equal to 1/2 mu naught Ni. Remember, this mu naught Ni is the magnetic field of an ideal solenoid like that. But then times cosine theta 2 minus cosine theta 1. What is theta 2 and theta 1? Theta 2 is the viewing angle of this end of the solenoid from the field point, and theta 1 is the viewing angle of the other side from the field point. And then we applied this equation to different situations. This is for an ideal solenoid. If you make that ideal, send this to infinity this way, this to infinity the other way, then theta 2 becomes 0, theta 1 becomes 180 degrees, and then cosine of theta 2 is 1, cosine of theta 1 becomes -1, and this equation reduces to this one that was for ideal solenoid. And if you have a semi-infinite solenoid, then you get this half of that ideal solenoid, as we expect, around actually semi-infinite, but the field point is at one end. And if you have a short solenoid at one end, you get 1/2 mu naught Ni times cosine of the viewing angle of that other end. And if you have a short solenoid at the center, which is the same as that figure, is mu naught Ni times cosine of theta. You see this cosine theta for that particular solenoid, you could calculate and see how much is smaller than an ideal solenoid by cosine of this angle. Of course, the larger it becomes, the longer the solenoid becomes, the theta becomes smaller, and therefore you get closer and closer to the field of an ideal solenoid. So this basically gives you a comprehensive value for every kind of solenoid. And then we talked about toroid, and that is this kind of distribution of currents. And we have this formula for that, mu naught Ni over 2 pi r. You can apply Ampere's law to get this result. And then these are the list of formulas we had for this chapter, minus the one that I found. I didn't include it here. And we went through this example that had 2 long straight parallel wires, 1 meter apart. As you see here, you see the cross section. The current of 6 amps going into the page through this wire that's perpendicular to the page. What must the magnitude and direction of the current I2 be for the net field at point P to be 0? And we did that. I asked you some questions. This is the way the field of 1 is. So it's like this, always perpendicular to the radial direction from perpendicular to the wire, right? This way. And in order for that current to have to cancel this, it has to have a magnetic field upward. So we said that the magnetic field should be upward, and the current, therefore, from right-hand rule, the current should be out of the page. And then we found the current to be 2 amps. And now we said that, okay, what is the in part B, and what is the magnitude and direction of the net field at point Q here? So this one creates a magnetic field up, and we can calculate that. The other one creates a magnetic field down. And of course, this one that's closer and larger current, it creates a larger magnetic field. So that the net magnetic field is up, and we calculated the net magnetic field to be 21.3 microtesla, and it's up. All right, and then we want to find the third part. What is the magnitude of the net field at S? At point S, this one creates a magnetic field that is perpendicular to the radial direction, right? And of course, given from right-hand rule. I put that in a question. I don't know if I should ask you these questions or not. Let's try one, see how you're doing. Which one is what is the direction of the magnetic field B1 of the current I1 at point S? Which one of these? All right, so about 57% of the answers in. Anybody else wants to answer? All right. All right, I think I ended right now. All right. So you see, this is the answers, and four people answered correctly. Very good. So as I said, for this current at this point, said that the magnetic field is perpendicular to this radial direction. So either this way or that way. So either C or F. And then from right-hand rule, if you put your thumb in the direction of the current, which is into the page, your four fingers show the direction this way, means shows clockwise direction around this. Therefore, the answer is F. So this is B1. And what about now the direction of magnetic field B2 of current I2 at that point? Let me give you the pose this time again, see if there is any improvement. All right, so answer this one. Now, what is the direction of the magnetic field of current I2 at this point?
So, Professor, just to make sure I have this right, when we point for the current, that's our pointer finger, right?
Yes.
And then
thumb in the direction of the current. Your four fingers shows the direction at which the magnetic field is circulating around that current element. All right, so I see some improvements. Please answer quickly. It shouldn't be that long. We have 50% of the answers in. Please answer quickly. All right. All right, this time is better. Now, eight people answered correctly this time so far. So let me end that and share the result with you. So 40% answered correctly. Again, I don't know why. Some people say C or D. D can be wrong using right hand rule, and C is completely wrong because it is never in the radial direction. And there's some, anyway. So the answer is, again, in this direction. So the answer was A. Again, if you put your thumb in the direction of the current, I2, your four fingers show which direction. Here, it shows this direction, counterclockwise. And at this point means this way, perpendicular to the radial direction. And the way these values, these distances are given, because this is 1 meter, this is 60 centimeter, and this is 80 centimeter. These happen, the field of I2 happens to be toward this I1, and the field of I1 happens to be in the direction of I2, but that is coincidence because this angle is 90 degrees. All right, so but if the angle is not 90 degrees, these don't coincide with each other. So be careful. This is just a coincidence. B1 is, we can calculate magnitude of B1, mu naught I1 over 2 pi R1. If you put the numbers in, mu naught 4 pi times 10 to the negative 7, I1 is 6, 2 pi 0.6 is the distance to I1. See this direction, this distance, sorry. So this 4 pi, 6 and 6 cancel, gives you 10 to the negative 6. 4 pi and 2 pi gives you a 2. 2 times 10 to the negative 6 Tesla, or 2 microtesla. And B2 is mu naught I2 over 2 pi R2, 4 pi times 10 to the negative 7 times 2 divided by 2 pi times 0.8. And this becomes half a microtesla. So, and if you want to find the magnitude and direction of the net magnetic field here, becomes the sum of these two vectors. Of course, in general, you should set up a coordinate system here and find x components and y components, add the x component, add the y components, and then find x and y component of total. And then from x and y component of the total, you can find the magnitude and direction of the total according to the x direction of your coordinate system. But here, because they are perpendicular to each other, you can say the magnitude here is B1 squared plus B2 squared. It happens to be like that. Here is the warning. In this problem, because of the specific numbers given, B1 and B2 happen to be perpendicular to each other. This is not the case in general. In general cases, we have to set up a coordinate system and go through the usual procedure of adding two vectors using components. Okay. So be careful about that. But here, because it happens to be, they happen to be perpendicular, we can say net is equal to square root of B1 squared plus B2 squared, which is 4 plus 2.25 microtesla or 2.06 microtesla. And the angle here, this is not the same angle that any problem would want, but if you have a coordinate system, then you can translate it to the angle to the coordinate system. Theta, this theta that's shown here is tan inverse of B2 over B1, which is tan inverse of 0.5 over 2, which is 1/4, and it becomes 14 degrees. But if you had an x direction here, for example, then you can find this angle between B1 and the x direction and add this theta to get the total angle from the x direction. All right. These are the answers. Any questions? All right. We're going to have more of these. This is another example. In figure, length A is 4.7 centimeters short and current I is 13 amps. What are the magnitude and direction into or out of the page of the magnetic field at point P? You have this point. We want to see what these the whole loop, what kind of magnetic field this whole loop of current create at this point. Any ideas? We can break that into 6 pieces. 1, 2, 3, 4, 5, 6. And then we need to figure out what kind of magnetic field each one of these pieces create at point P. For example, what is the direction of the magnetic field of the segment 1 at point P? Let's see if I give you the poles. Oops. We launch. All right. What would you answer? A, B, C, D, E, or F? I hate to bet against you, but I don't think anybody would answer correctly this one. Oh, somebody did. All right, it shouldn't take that long, please. Answer quickly if you want to. All right. Yes, that's everyone, almost. All right, I'm going to end the poll and share it. Does anyone want to share their thoughts about how they got the answer? See, the answers are all even between B, C, D, and E. B, C, D, and E. Anyone wants to talk about it?
For me, because the way I was looking at it, the current's the same direction, right? Like no matter where you have on the wire, it's still going up, right?
The current in this piece, the part 1, segment 1, is going to the left.
Oh, I see. So it'd be.
So, what do you think?
Oh, all right. So if it's at 1, then if it's going left, wouldn't that be away from us, right? So
yeah.
E.
All right. So who answered F? Only one person answered F. Everybody answered A, B, C, B, C, D, E. Pretty much evenly.
Hello, Professor.
Yeah.
So for the first one, the current's going to the left, but the 4 fingers are not on the point, so it's undefined, right?
Undefined because what? Why is it undefined? Did you answer that?
Well, yeah, but is it because it's perpendicular or?
No. We said that, you see, each element, all right, I'll explain. Each element of current you see here, remember we said that when there's an element of current here, for each element of current, the magnetic field here is 0 because this going right behind the current or right in front of it. The cross product in the definition becomes 0.
I see. So when the current's always in front of the point, it's always 0.
Yeah, when the current is going away from the point or going toward the point, the field is 0 for that current, and therefore, when the magnetic field is 0, there's no definition for the direction. So undefined is correct. F is correct because there's a magnetic field at that point for segment 1 is 0. I mean, due to segment 1. All right. All right. So now, what is the magnetic field of 2? Let me see if I have the. So that, sorry, the answer was that. And what is the magnetic field of the segment 2 at that point? Which one is it? Let me give you a poll again. So this one is getting better a bit. All right. It shouldn't take that long. Just put your thumb in the direction of the current downward, and then you see that the magnetic field is circulating. And if you are to the left of the current, the magnetic field is going into the page. The right of the current going out of the page. So the answer, therefore, is out of the page. E is the correct answer. Okay, that's the most popular answer. We're making improvements. All right. So the answer is E. Again, you put your thumb in this direction, your four fingers go into the page here, go out of the page here. And because this should be perpendicular to the radial direction, it will be perpendicular to the page, out of the page. So it will be E. And what about for part 3? Somebody shout. Part 3. Somebody shouted. Yeah. That's also E. Again, if you put your thumb in the direction of the current this way to the right, you see that your four fingers show coming out this way, this side, coming into the page here. And this is on the top side, it comes out, so it becomes E. So that's the answer is E. Again. 4. This one, what do you think? Yeah. Yes, I see some F. That's correct. Again, the current is going through the point and it doesn't create any magnetic field right in front of it. So when the magnetic field is 0, the direction is undefined. And for 5, the answer, okay, people are very good. You're saying D. Again, you put your thumb in the direction of the current, which is to the left, and your four fingers go into the page at point P, so it goes into the page. So D is the correct answer. Very good. You guys are getting hold of it now. All right, and then for 6. So for 6, also D. Very good. All right, so you guys are getting hang of it. So 2 and 3 create a field that is out of the page. 5 and 6 create a field that's into the page, and 1 and 4 create no field at that point. So basically, if you want to find the net magnetic field here, you should add these two and then add these two and then subtract the results, right? So there are 2 into the page and 2 out of the page. And now, which one of the following formulas is best to use to find the net magnetic field at point P? You see, I gave you the list of formulas. Can you answer this now? Let me relaunch. Which one of these formulas are suitable, the most suitable, easiest to use for this problem? If you remember what the formulas were, you can decide very easy. From the shape of the formula, you can probably know which one is the best, or what each one is for. All right. Anyone else wants to answer? All right. Any last minute answers? All right. I'm going to end it soon and share the result. All right. So these are the distribution. Okay, the first equation is Biot-Savart's law. It can be applied to anything, but you have to integrate. It's okay. You have to integrate. The second one is for infinitely long wire. We don't have an infinitely long wire here. So B is not the answer. And C was for what? Let me see if I have that here. Yes, you see, this is the C. We said for the short straight wire, perpendicular to one distance r perpendicular to one end of the wire. So this is what the situation we have here. For example, for this 6, you see perpendicular distance to one end, and it is at distance A. And of course, it happens that the length of the wire is also the same A. Okay. And so that is the answer. C is the answer. This one was for a ring, right, at the center. This was for an arc. Remember, I just corrected it. Phi over 2 pi r, phi over 2 pi. This was for an arc of angle phi. This one was for the coil on the axis of the coil. There's no coil here. All right, so the answer is C. All right, from this equation. This was for long straight wire. See, that was B. This is C. All right, so the answer is this one. And now the question is, how do we answer or calculate? If I want to use that formula, mu naught I over 4 pi r. So let me write down the formula here. We have B equal to mu naught I over 4 pi. I don't like my writing, just let me. Mu naught I over 4 pi sine of theta. Well, we need to 4 pi r. We need to know what is r, what is theta, and of course I is given. I is 13 amps. What is r? What is sine theta? Remember, r was perpendicular distance to the end of the wire. So this is r for 6. So B6 is mu naught I over 4 pi A times what is sine theta? Remember, sine theta was the angle, viewing angle of the whole wire for this. So theta is what?
45.
Yes, theta is 45 degrees. And sine theta is square root of 2 over 2, which is 0.707. All right, so this becomes 0.707. All right, and A is given also. So this is B due to 6, the segment 6. What about 5? B5. You see the perpendicular distance to the end is this R. the same as A, isn't it? And the angle is also 45. So it will be the same. B5 will be the same as B6. So we can say B5 and 6 together is 2 times B6, which is, we can say mu naught I over 2 pi A times 0.707. All right. So this is 5 and 6 together. And was it into the page or out of the page? That was into the page. All right, this is for 5 and 6. What about for 2? For 2 and 3. For 2, the distance to the end, this is R2, let's call it. This is R6, this is R5. R for 2 is perpendicular distance here, right? And which is 2A, right? And theta is again the same, right? So for 2, B2, which is mu naught I over 4 pi, the distance R, which is 2A, times sine of 45, which is 0.707. And this is the same for B3. And you see B2 equals B3 equals 1/2 of B6, because there's a factor of 2 here, and 1/2 of B5. So, and then this is B2 and B3 is out of the page. Sorry, into the, yeah, out of the page. All right. So you see these two add up and cancel some of the B5 and 6. So we have B5 plus B6. These two add up and cancel one of B5. So the net result is the same as B6, right? Because like you have B2 and B2 and B6 and B6, but B6 is twice B2. So if you cancel, the net will be B net is equal to B6, which is this mu naught I over 4 pi A 0.707. You multiply that. You can calculate. You put I equal to 13, A equal to 4, let me write it, 4 pi times 10 to the -7 times 13 divided by 4 pi. 4 pi is cancel times 0.047 and 0.707. All right, so this 4 pi cancels, becomes a number. Can calculate. All right. So this is the solution to this problem. This is the whole thing. B net is this. All right. Okay. This is another problem. Again, all right. If I want to calculate that, I can use the same equation. You see, at this point, first of all, which direction is the magnetic field? Or you can continue this line, continue this line here, and continue this line here, and you can break it into 8 pieces. Oops, I need a ruler here. And break it into 8 pieces like that. And each piece, you see, we have perpendicular distance and an angle. perpendicular distance and an angle. Perpendicular distance and an angle. And we have like, how many angles? We have 45 degrees here. For these is 45. So for these two, we have two different angles. So there are three different angles in total. And you can see that, all right, let me make it easy. So let me call them 1, 2, 3, 4, 5, 6, 7, and 8. And you see 1, 3, 5, 7 is the same as 2, 4, 6, 8, right? So we can just calculate the odd numbers and then add the even numbers. All of these from right-hand rule. For example, in here, if the current is going this way, you put your thumb, you see that the thumb in that direction to the right, you see that the field of that is going into the page at point P. If you do the same here, the current is going up, the field is going into the page. For all of them, the field is going into the page. So all of them add up like numbers, okay? Because they are all in the same direction into the page. So B net is equal to 2 times B1 plus B3 plus B5 plus B7. All right, now we can calculate all of these. B1 is at 40, the angle is 45 degrees, so it becomes mu naught. I is 10 amps, divided by 4 pi. A is 8 centimeter times 0.08 times sine of 45 degrees. All right. And B3 is mu naught I over 4 pi R, which is again 0.03. No, sorry, A is 0.03. A is 0.03. This distance here is 1/4 of A, so it becomes 1.02. In this case, also 0.02, and this angle, sine of this angle, let's call it θ3. And you see that sine of θ3 is adjacent over hypotenuse. Sine of θ3 is adjacent, which is A over 3 divided by square root of A over 3 squared plus why A over 3, A over 4, sorry. A over 4 divided by A over 4 squared plus 3A over 4 squared. And you see here, I can multiply both numerator and denominator by 4. So I get A divided by 4 goes into the denominator, into the square root, and cancels all the 1/4 squared. So it becomes square root of A squared plus 9A squared. So A comes out here, cancels, becomes 1 over square root of 10. Sine θ3 is 1 over square root of 10 from geometry. All right, and then what is this is B3 and B5. B5 has this angle, θ5. What is sine of θ5? Becomes 3 divided by square root of 1 squared plus 3 squared. So sine of theta 5 becomes 3 over square root of 10. And then the distance here, R5, is 6 centimeter. So mu naught I over 4 pi times 0.06 times 3 over square root of 10. All right. And does it mean that they have the same? Oh my gosh, I made a mistake. Sine of theta 3 is opposite over adjacent. So this is 3. So it becomes 3, it becomes 3. This becomes 1. I'm sorry, my mistake. So B3 is much bigger than B5. And then B7 is, let me write here, B7 is mu naught I over 4 pi. Distance is 0.06 again. The angle is 45. So you add all of these, multiply by 2 becomes net magnetic field. And you see mu naught over 4 pi here becomes 10 to negative 7 times 10. That becomes a micro times 3 over 0.02 square root of 10, or 300 over 2 square root of 10. So that's 300 over 2 square root of 10 microtesla here. And here is 9 times smaller. 10 to negative 6 times 300 over 18 square root of 10. And what is this? Becomes 10 to negative 7. That's mu naught over 4 pi times 10, again micro, and times 1 over 0.02. That becomes 50 microtesla. And this one is 1/3 of that, is 50 over 3 microtesla. All right. So you can calculate the whole thing. I think you can manage the rest. All right. Any questions? And now this figure, a closed loop carries current 200 milliamp. The loop consists of 2 radial straight wires, means these 2 pieces, and 2 concentric circular arcs of radii 2 meters and 4 meters. All right. The angle theta is pi over 4. It looks like pi over 2 radian. What are the magnitude and direction into or out of the page of the net magnetic field at the center of the curvature P? So, what are the magnetic field of these 2 straight parts? What do you think? You see the current is going this way or going this way, right through the point P. So the for those pieces, the magnetic field is 0. The direction is undefined, but the magnetic field of these 2 parts is 0, right? So we don't forget about these 2. They don't create any magnetic field at point P. But in order to find the magnetic field of the other arcs, which one of the equations are useful, the most useful?
E.
E, very good. Yes, we did. We said that this is for a circular arc. That's the answer. Thank you. All right. So this is the answer. This is the equation we need to use. And how do we use it? We have two pieces. What is phi? What is r for that piece? Let me call this piece number 1. This is number 2. So this creates B1 and B2. Which direction is B1? So the current B1 is in this direction. Current of 1 is in this direction. Does it create a magnetic field into the page or out of the page? If you use right-hand rule, either way, we get a magnetic field into the page. So B1 is into the page and B2 is out of the page. Okay. So, but what is the magnitude? We can find B1 here. B1. If I want to use this, mu naught I over 2 pi, 2r, sorry, 2r. What is the r? R for 2 meters and 4 meters. 2 times 2 for B1. And phi is the angle, this angle. If this is pi over 4, what is this? Let's call it theta 1.
3 pi over 4.
No, it should be 2 pi minus pi over 4.
Oh, sorry. Oh, yeah.
Yeah, so 7 pi over 4, right? 8 pi over 4 becomes 2 pi. This has 1 pi over 4 less. So 7 pi over 4 over 2 pi. Right? So pi cancels out. So it becomes 7 mu naught over 2 times 2 times 2 times 4. 32. Times I is 0.2 times 0.2. All right, so this is B1. And for B2, I write it right here. B2 has a magnitude mu naught I over 2 times 4. And the rest is the same, 7 pi over 4 over 2 pi. So it's exactly the same as that, but it has a 4 in the denominator instead of 2. So it becomes half of B1. So B2 is equal to half of B1. B net is a B1 minus B2. B2 is half of B1, so B net becomes the same as magnitude of B2. One of them cancels and is into the page. Okay, make sense? All right. That's the magnitude and that's the direction. All right, let's move on here. Figure shows a cross-section of a long conducting coaxial cable and gives its radii A, B, C. The coaxial cables that you see in the market, they kind of are like this. Equal but opposite currents I uniformly distributed in the two conductors. Derive expression for B as a function of R with radial distance R in the ranges R less than C or R between C and B and between B and A and greater than A. So we want to find the direction of the magnitude of the magnetic field at different distances. So for here, when I want to do this, I just calculate the magnetic field on the surface of this inner conductor. Because the outer conductor doesn't, but according to the Ampere's law, doesn't affect the magnetic field here. And we can calculate the magnetic field at this point. Let's say the current in here coming out. And therefore the magnetic field at this point is B. Let's call it B naught. Then B naught becomes mu naught I, whatever current there is for each one of them, divided by 2 pi the radius C. All right, this is for the surface. We said that anywhere inside, it will be linear from 0 to the surface. So it means B1, let's call it, is mu naught I over 2 pi C and R over C. Right? Because this is linear. If you put R equal to 0, it gets 0. If you put R equal to C, you get the same as B naught. So this is for R less than C, part A. For part B, which is R between C and B, means around here, we can apply the Ampere's law, but you don't have to. You can use the result of what we found in here. We said that B, let's call it B2 at this point is B2. B2 is equal to mu naught I over 2 pi C. Instead of C, we have 2 pi R, because outside just works like a thin wire. So this is when R is between B and C. So that's part B. Part C, it says R between B and A, means at this point. At this point, the magnetic field is this way. It is composed of the magnetic field of the middle one plus the magnetic field created by this part of the wire. Because the outer side, these parts don't create any magnetic field because of Ampere's law. All right. So for this part, we can say, okay, what is the total charge? We can apply Ampere's law. Say, if we apply Ampere's law for this Amperian loop that is shown in the figure, this is Amperian loop. If we write for that, we said integral of B dot ds or dl equal to mu naught times I total that is inside. So again, we argue that B and dl are in the same direction. So B becomes B times dl, and B is the same everywhere. B comes out. So we become B times integral of dl, which is 2 pi R. R is now this distance that is also shown in the figure. This is R. Equal to mu naught I total. The I that is passing through this loop. How much is that? There is this I going in and this I total going out out of the whole cross section. But we need to find the current in here. That is the hard part. So this one creates this I from the middle one creates a let's say take that as positive. Let's call this I2 that goes into here. So this becomes mu naught times I minus I2, right? I from the middle minus I2. And how much is I2? To find I2, we say that I2 over I is the same as the area of this part that I actually scratched, A2 over the total area of that cross section of that wire. So the A2 is what? What is the area of that part that I shaded? This part that I shade. What is the area of that?
2 pi r minus 2 pi b.
Very good, but not 2 pi r. We are talking area. Try again.
Pi r squared, sorry, minus
That's
pi
right.
b squared.
Pi r squared minus pi b squared. What about total area?
Pi a squared.
Pi a squared minus pi b squared, right? The total area of the outer shell. And you see that pi cancels out. And therefore, so let me write this I, the I2 over I becomes r squared minus b squared divided by a squared minus b squared, right? And if you multiply by I, you get I2. I2 is equal to r squared minus b squared over a squared minus b squared times I. And then if you put it in here, so this becomes mu naught. You can factor I, let me factor I, because both of them have I, 1 minus r squared minus b squared divided by a squared minus b squared. So let me separate this now. So here, 2 pi r b becomes mu naught I. If you make common denominator here, 1 becomes a squared minus b squared divided by a squared minus b squared. So we have a squared minus b squared here. And then we have a squared minus b squared minus r squared plus b squared. So it becomes a squared minus r squared. Okay. So now you see that you have to find for B, let me call it B3 in the third region, becomes mu naught I over 2 pi r times this expression, a squared minus r squared divided by a squared minus b squared. And then if you consider special cases, for example, if what happens if r is equal to a, now r is equal to b. If r is equal to b, means you are at the inner surface of the outer shell. Let me clean up here. If r is equal to b, what happens? So if r is equal to b means that you are here. And of course, the outer shell doesn't create any magnetic field there. The whole magnetic field will be that of the inner cylinder. And if you put r equal to b, you see that this fraction becomes 1, becomes mu naught I over 2 pi b, right? So that's the magnetic field of this one at this point, which is correct. What if you put R equal to A? It means that you are in here. You get A squared minus A squared divided by A squared minus B squared. Right, you get 0, because if you take if you expand this Amperian loop to become this circle, the total current passing through it is 0, right? Because current in here coming out, in here coming out, in here going into the page. So the total current is 0. Therefore, from Ampere's law, the total magnetic field will be 0, which is again given by this equation. And if you go out at this, if you take my Amperian loop larger outside, again, the total current going through is 0. Therefore, magnetic field is 0. So in the fourth region, in part B, the magnetic field is 0. So B4 is 0. All right. That's why they do coaxial, because if the magnetic field is 0 outside, the magnetic field outside doesn't affect the current inside either. Right? So if you have that in electromagnetic waves, that doesn't affect the current inside, therefore, you know, the signal that you're sending through it doesn't get affected by electromagnetic waves. That's why they make coaxial wires. Okay. And test these expressions for all the special cases. That's just what I did. Assume that A is equal to 2 centimeter, B equal to 1.8 centimeter, C equal to 0.4 centimeter, and I equal to 120 amp, and plot the function over the range of 0 to 3. So it says outside is 0. You can say the plot goes like this, from 0 to that, and then it goes like that, and then goes like this, something like that, and then after that will be 0. All right, you can do that. We have 1 minute left. I want to just comment on this. There are cross section, 2 long parallel wires that are separated by distance d. Each carries 4.23 amps out of the page. So both of these are going out of the page. We want to see, oh no, wire out of the page in wire 1 and into the page for wire 2. So this one is like this. In unit vector notations, what is the net magnetic field at point P at distance R here? All right, so again, you see, we have 2 currents, long straight wires. The formula is mu naught I over 2 pi R for each one. R is the perpendicular distance, which is the same for both of them, which you can find from Pythagorean theorem. All right, so what is the direction? See, the direction of magnetic field of 1, we call it B1, is perpendicular to this radial direction. I need a more precise figure. Perpendicular to this radial direction. So it will be like that. And is going counterclockwise from right-hand rule. And the magnetic field of this one, 2, will be perpendicular to this direction, which is this way. So the x components cancel out, the y components add up. All right. So you need to calculate now the net magnetic field. This is B1, this is B2. All right. So because of symmetry, they cancel the x component, the y components add up. So the direction is right up. All right. This is B net.
Professor, quick question for 2. Isn't it down because it's going into the page?
Yes, very good. Yeah. Thank you. Yeah, my mistake. It is this way. So then B net is not that way. So it will be perpendicular to this again. You see, here is it perpendicular. Here is this way perpendicular. And then their y component cancels. B2 here, the y component cancels. The x components add up, so B net. Yeah, very good. I made a mistake. Thank you for mentioning that. All right. All right, that's it for this chapter. And next time we'll start the next chapter on Thursday. On
Thank you,
Wednesday.
Professor. You have a good day.
You too.
Thanks,
Fantastic,
Professor.
Professor.
Have a good night.